When we look up at the night sky, we see a dense canvas of stars. But that view is incomplete. Much of the history of our universe is happening in the infrared, a spectrum that is invisible to human eyes. To see the events that shaped our cosmos, we have to stop looking for the light we can see and start sensing the heat we can't. That is why the James Webb Space Telescope was built. It is a specialized heat sensor engineered to detect invisible thermal radiation from deep space. Shifting our perspective to infrared heat is the only physical way to see through cosmic dust and find the hidden origins of the universe. Since Galileo first pointed a telescope at Jupiter in 1610, astronomers have relied primarily on visible light optics. While we eventually developed tools to see radio waves and X-rays, a massive gap remained in our ability to observe the faint, heat-based signatures of the early universe. Webb was designed to close that gap with two primary targets: capturing the light of the very first galaxies and searching for chemical signatures in the atmospheres of distant planets. This mission gives humanity a new way to observe the cosmos, allowing us to see the specific physical processes that lead to the birth of stars and planets. But building a heat-sensing telescope in our solar system is a massive engineering challenge. Our local space environment is constantly flooded with heat radiating from the sun, the Earth, and the Moon. You cannot solve this from the ground. Earth's own warm, dense atmosphere blocks and distorts these faint thermal signals before they can reach a telescope on the surface. Even the Hubble Space Telescope, operating above the atmosphere, was built primarily for visible light. Its internal temperature is too high to detect the deepest, most distant infrared signals. This created a bottleneck. To capture ancient heat from the dawn of time, the telescope's own internal components cannot be allowed to radiate heat that would wash out the image. To see these signatures, engineers had to build a machine capable of operating at temperatures just a few degrees above absolute zero. The solution began with a 6.5-meter mirror made of 18 hexagonal segments. These are crafted from beryllium, a metal chosen because it is both lightweight and remains stable at cryogenic temperatures. Each segment is coated in a layer of pure gold, just 1,000 angstroms thick. Gold is used because it reflects over 98% of incoming infrared light, ensuring that almost every photon reaching the mirror is captured. To keep that gold mirror from overheating, engineers developed a 5-layer Kapton sunshield, roughly the size of a tennis court. This shield reflects raw solar radiation on the side facing the sun, where temperatures reach 358 Kelvin. As heat moves through vacuum gaps between layers, it bleeds off into space. By the time it reaches the optics, the temperature drops to just 40 Kelvin. This extreme sensitivity allows Webb to detect the thermal signature of a single bumblebee at the distance of the Moon. This thermal isolation is the physical requirement for registering light that has been traveling for over 13 billion years. Once the mirrors capture that light, it is processed by the near-infrared spectrograph, or NISPEC. This instrument breaks light apart into its individual wavelengths, functioning as a chemical analyzer for the cosmos. It uses a technique called transit spectroscopy. When a planet passes in front of its star, a small portion of the starlight filters through the planet's atmosphere on its way to Webb. Analyzing the patterns in these blue and green dots reveals the chemical composition of distant atmospheres. A spike in this specific region confirms molecules like water, methane, or carbon dioxide, the essential building blocks we look for when assessing if a world could support life. While it searches for life across the galaxy, Webb is also providing a new look at the objects inside our own solar system. It is actively mapping the atmospheric bands of gas giants like Jupiter and tracking the orbits of icy asteroids in the distant Kuiper Belt. Webb is providing high-resolution chemical maps of our local neighbors, while simultaneously identifying the potential for habitability on worlds orbiting other stars. All of these observations rely on the fact that light takes time to travel across the vacuum of space. To see far away is to see back in time. However, because the universe is expanding, light waves from the most distant objects are physically stretched as they travel toward us. This process, called redshift, turns ancient visible light into invisible infrared heat. Because of this stretching, the very first stars and galaxies can only be seen by a telescope designed to capture that specific infrared energy. There is a limit to how long we can watch. Webb orbits 1,000,000 miles away at Lagrange Point 2, where it cannot be serviced. The mission will end when it exhausts the fuel required to maintain its orientation. But for now, the telescope is providing the first detailed look at the era when the first structures in the universe began to form. By isolating these ancient heat signatures, we are finally observing the very first structural assembly of our cosmos.